There are moments in history when the conventional wisdom of a great power turns out to be its fatal blind spot. And for Adolf Hitler and his generals, that blind spot was American ingenuity. They saw our initial performance with artillery as clumsy, inefficient, and riddled with technical flaws. They laughed, literally, at what they perceived as our mechanical incompetence. You see, the early war reports sent back from the Wehrmacht, from the Afrika Korps and the European fronts, were full of anecdotal evidence about how often American and British fuses either failed to detonate or exploded harmlessly miles from their targets. They looked at our manufacturing and our engineering, particularly in munitions, and they concluded that their own deep-seated technical superiority guaranteed them a decisive edge on any battlefield. But what the German High Command didn't know, what they couldn't possibly know, was that this widespread failure rate wasn't a sign of engineering weakness, but the perfect cover for one of the most critical, most lethal, and most heavily guarded secrets of the entire war. I'm talking about the proximity fuse. It was an invention so revolutionary it fundamentally turned the tide of battle, transforming our standard artillery from a blunt instrument into a silent, deadly precision weapon. General George C. Marshall himself, the Army Chief of Staff, would later rank the proximity fuse, often referred to by its operational name VT, as one of the 3 or 4 absolutely essential scientific developments of the entire war, alongside the atomic bomb and radar itself. Now think about that for a moment. They put a device that detonated based on proximity, based on sensing the target, in the same league as splitting the atom. But why? Why was this small piece of metal and glass considered a world-changing weapon? The difference was simple but devastating. Prior to the VT fuse, artillery relied on contact fuses or precise time delay settings. You either had to score a direct hit on a target or you had to guess the exact altitude and time it would take a shell to explode above a formation. This worked well against stationary targets or ships, but against advancing infantry, especially under cover, or against high-speed aircraft, it was a game of chance. The odds were against us. The proximity fuse changed the odds. It meant a shell exploded not when it hit something, but when it sensed something nearby. This capability meant that every single shell fired created an enormous sphere of lethal, descending shrapnel, effectively turning every single shell into a lethal, shrapnel-spewing shotgun blast fired high in the air. If you're finding this deep dive into the hidden history of World War II intriguing, many viewers tell us that liking this video is the simplest way to let us know you want more of these untold stories from that era. The challenge wasn't just in the design, it was in the execution. How do you take a complicated, fragile electronic circuit and jam it into a shell that fires out of a cannon? This is where the story of the proximity fuse truly becomes one of American defiance against the limits of physics. They had to create a miniature radar system that could survive 20,000 Gs of force and 18,000 RPMs of spin. They forced fragile vacuum tubes to survive where only steel had gone before, using clever construction and a special wax filling. This was a deliberate act of engineering defiance, ensuring the weapon would work when it mattered most. And it was all done behind a perfect smoke and mirrors curtain of supposed failure.
The German High Command's misjudgment of our technical failures was a fatal mistake. They were so focused on their own precision that they couldn't fathom a weapon that transcended the need for it. The true genius wasn't just building the fuse, it was hiding it in plain sight, using a genuine problem as the cover for a secret that would ultimately secure victory in the Battle of the Bulge and beyond. The sheer audacity of the idea, at the time, was breathtaking. We were fighting a war defined by tanks and infantry, but the next battlefield was electronic, and the weapon was something the enemy and even most of our own troops couldn't imagine. A miniature, functional radar system packed inside an artillery shell. This wasn't science fiction. It was the proximity fuse, and the journey to build it was a brutal contest against the fundamental laws of physics and engineering. The initial challenge was so overwhelming it might have stopped a less determined group. The mission, given to a dedicated team of scientists and engineers, was to achieve what everyone thought was impossible: survival. Think about the physics involved. A shell fired from a 105mm howitzer goes from 0 to high velocity in a millisecond. In that tiny fraction of a second, the entire payload is slammed with an instantaneous force equivalent to more than 20,000 Gs. If you've ever experienced the pull of a modern fighter jet, that's maybe 9 Gs. This tiny, complex fuse had to survive a force more than 2,200 times greater. This extreme shock was why the early prototypes of electronic fuses were failing almost instantly. The standard electronics of the 1940s, fragile vacuum tubes and delicate wiring, were simply not designed for this kind of violence. The glass tubes would implode, the filaments would snap, and the wiring would tear itself loose. Hitler and his generals had a genuine basis for their ridicule. Our early attempts were failing at a staggering rate. The challenge wasn't to invent a radar, but to invent radar electronics that could laugh off 20,000 Gs of shock. The engineers realized quickly that they couldn't just reinforce existing components. They had to re-engineer the core technology of the electronic age itself. The primary culprit was the vacuum tube, the ancestor of the modern microchip. These were delicate, glass-enclosed structures, and the impact force of firing a shell was effectively trying to squeeze that fragile glass into dust. They needed a tube that was robust enough to handle the initial launch, yet sensitive enough to still transmit and receive a faint radar signal mid-flight. The solution came from a dedicated team of researchers at the Johns Hopkins University Applied Physics Laboratory, APL. They developed a series of specialized, miniature vacuum tubes that were radically different from standard commercial designs. These tubes were built inverted, with all the components meticulously compressed into a small, rigid package, often described as being about the size of a man's thumbnail. Crucially, the internal elements, the grids, plates, and filaments, were braced and held in place by mica spacers and a meticulous, highly compressed construction process. This compression minimized the space between components, making the tubes structurally solid rather than hollow. This ingenious modification essentially turned a fragile glass balloon into a tiny electronic brick. It was a staggering feat of miniaturization and ruggedization that had profound implications far beyond the battlefield. But surviving the initial shock was only half the battle. Once airborne, the shell wasn't just coasting, it was spinning furiously. The high-velocity twist imparted by the rifling grooves inside the gun barrel caused the shell to rotate at speeds approaching 300 revolutions per second, or nearly 18,000 RPM. This rapid rotation subjected all the internal components to massive centrifugal forces, the same force that pins you to the wall on a carnival ride, only magnified hundreds of times. This was enough to slowly, inexorably tear the wiring and electronics away from their mountings, leading to a late-flight failure, another dud that would bolster the enemy confidence. The APL engineers devised a truly elegant countermeasure. They meticulously filled the remaining empty space inside the metal shell casing with a specialized dielectric wax compound. This wasn't just for padding. The compound was introduced in a liquid state and then solidified, acting as a rigid internal support structure. It encased the sensitive electronics, the tiny tubes and the essential wiring, holding them firmly in place. This wax compound acted like an anchor, physically locking the entire circuit board into a solid block that could resist the immense centrifugal forces of the spin. The fuse couldn't just fire. It had to stay functional for the 20 to 30 seconds it took to reach its maximum range. This painstaking process required a new level of precision manufacturing, ensuring that the wax filled every void without damaging the sensitive radar components. Now, let's address the core function. How did this tiny device actually work as a radar? The principle was deceptively simple. The proximity fuse shell incorporated a nose cap that doubled as a miniature antenna. Inside the shell, the miniature transmitter constantly emitted a radio frequency signal, a faint, invisible electronic bubble that pulsed out ahead of the projectile. This pulse created a stable, measurable energy field around the traveling shell.
When the shell approached any solid object, a plane, a tree canopy, or a column of infantry, that object reflected the radio signal. This reflected signal returned to the antenna, causing a tiny but measurable change in the electrical field. This change was then detected by a small amplifier built into the circuit. When the amplifier registered a signal strength that indicated the shell was within a lethal distance, typically 50 to 70 feet, it instantaneously triggered the detonator. The warhead exploded, unleashing a massive cone of deadly shrapnel downward. The time delay was measured in microseconds, achieving a level of instantaneous accuracy previously unheard of in field artillery. This ingenious method meant the gunners no longer had to rely on direct hits or perfect time-setting estimates. They simply had to get the shell near the target. For artillery facing entrenched troops, this transformed their effectiveness. A standard shell might hit the ground and only take out a few square feet. A proximity-fused shell detonating 50 feet above the ground could blanket hundreds of square yards with lethal shrapnel. This difference was a literal game-changer, multiplying the effectiveness of every artillery piece on the battlefield and fundamentally proving that American intellectual effort could be a far more potent weapon than the enemy's perceived material strength. The final layer of protection for this incredible technology, however, lay not with the scientists, but with the oceans themselves, a story that shows just how high the stakes really were. The successful engineering and miniaturization of the proximity fuse was, without question, a monumental achievement. The engineers had wrestled with the brutal physics of acceleration and rotation and had forced fragile electronics to survive where only solid steel had gone before. But achieving technical readiness did not translate immediately to battlefield deployment. In a curious and agonizing paradox of the war, the weapon that promised the greatest advantage was initially held back from the most desperate ground fighting, and the reason for this restraint reveals the true weight of the technological secret we possessed. The problem, which overshadowed every tactical need, was the risk of enemy recovery, the nightmare scenario of a dud fuse being captured and reverse-engineered by the Germans. If the enemy discovered the variable time VT principle, that a shell could actively seek and sense its target using miniature radar, they could instantly deploy countermeasures, nullifying our advantage. Worse, they could swiftly reproduce the technology and turn it against us, eliminating our exclusive edge. Therefore, the Allied High Command, acutely aware of the devastating consequences of losing this secret, enacted a policy of extreme caution that prioritized strategic security over immediate tactical gain. This policy gave birth to the concept of the ocean's cloak. For the first critical years of its existence, the use of the VT proximity fuse was strictly limited to naval warfare. Why the oceans? The reason was as simple as it was brilliant. The sea offered guaranteed destruction of a failed device. If a shell was fired and failed to detonate, a mechanical failure or a simple misfire, it would plunge deep into the crushing abyss, its advanced electronics and highly classified design sunk forever. The water served as a vast, inescapable vault, protecting the secret that would eventually save the lives of countless soldiers on land. The first major proof of this sea-based dominance came not from offense, but from defense, specifically against the Japanese during the Battle of the Philippine Sea in June 1944. This engagement, which the Americans famously dubbed the Great Marianas Turkey Shoot, highlighted the lethal effectiveness of the VT fuse against aircraft. Japanese naval air groups, expecting conventional anti-aircraft fire, were instead confronted by a vast invisible wall of air-bursting shrapnel. The VT fuses, detonating precisely when they sensed an aircraft nearby, decimated the Japanese formations.
pilots reported that the American fleet was enveloped in an inescapable continuous barrage that exploded seemingly at random without the need for accurate spotting. The kill ratios climbed dramatically, demonstrating that the future of air defense lay in this new electronic battlefield. But this naval success created a deepening irony and tension on the European front. Our sailors were protected by this miracle weapon, but our soldiers fighting in North Africa, Sicily, and France were still grinding out battles with old-style contact fuses, resulting in frustrating losses of men and materiel. General Dwight Eisenhower, then the supreme commander of the Allied Expeditionary Force, pressed for its immediate release for ground use. He faced immense pressure from commanders desperate for a technological edge against entrenched German defenses. However, the Joint Chiefs of Staff continued to deny the request. The risk of the secret falling into German hands, particularly given the proximity of our front lines to German industrial centers, was deemed too great to compromise. The policy finally cracked under the pressure of a new, desperate German threat, the V-1 flying bomb campaign against London in the summer of 1944. This pilotless, high-speed missile presented a unique and terrifying challenge that our conventional anti-aircraft guns could not effectively counter. The V-1s flew too fast and too low, overwhelming traditional fire control systems. The need to defend the British homeland, a political and strategic imperative, forced the first major exception to the Ocean's Cloak. The VT Fuse was authorized for use by land-based anti-aircraft guns defending London and Antwerp. The key legal and security distinction was once again the geography of failure. If a V-1 was shot down, the dud shell would land in Allied territory, where recovery and destruction could be guaranteed. The results were immediate and astounding. Prior to the VT deployment, the kill rate for these fast-moving threats was abysmal. After, it climbed to over 70%. The Fuse effectively neutralized the V-1 as a terror weapon, providing tangible proof of its overwhelming power on land.
But this tactical victory defending the rear lines only served to escalate the psychological warfare on the front. Soldiers huddled in trenches were well aware that a technology existed that could save their lives, yet they were forbidden from using it because of an intelligence risk. The situation became a ticking time bomb of desperation. The moment the Germans launched their last great counteroffensive, a massive gamble through the frozen, fog-shrouded Ardennes forest, that delicate tension between protecting the secret and saving the soldier finally snapped. The proximity fuse was about to be rushed to the front, not because the security concerns vanished, but because the stakes of losing the battle had finally exceeded the stakes of losing the secret. This was the moment the weapon earned its legend. The Battle of the Bulge, or the Ardennes Counteroffensive in December 1944, was a desperate, calculated gamble by Hitler. The German High Command knew their chances of winning a war of attrition were gone. Therefore, they pinned their last great hope on a single, massive surprise attack designed to shatter the Allied lines and divide their forces. But the success of this audacious plan didn't hinge solely on tanks and infantry. It relied almost entirely on a silent, invisible ally, the weather. The moment a blanket of thick, miserable fog, heavy snow, and freezing rain descended upon the Ardennes forest, Hitler's plan was activated. Why was this bad weather considered such a strategic advantage for the Wehrmacht? Throughout 1944, Allied victory had been guaranteed by air superiority. Our fighters and bombers, the eyes of the army, controlled the skies, providing intelligence, breaking up enemy concentrations, and providing tactical air support. But the fog and snow, however, achieved what German anti-aircraft guns could not. It grounded our air forces completely. Without our eyes in the sky, the American High Command was essentially blind, unable to track the massive German troop movements in armor columns surging through the dense forests. This forced our ground forces to fight deaf and blind, relying solely on ground intelligence that was often inaccurate or delayed. The German calculus was proven right in the opening days of the attack, creating a tactical nightmare for our key advantage, field artillery. Our most potent equalizer, the massive concentration of American artillery fire, suddenly became almost useless against the advancing enemy. Think about the mechanics. Conventional artillery doctrine relies on precision. You must accurately observe where the enemy is, a job usually done by airborne spotters, or you must fire at pre-registered, fixed ground coordinates. But in the chaotic, obscured conditions of the Bulge, neither was possible. The enemy was moving, hidden by fog, snow, and the dense pine forest. Our gunners, therefore, were reduced to blindly firing into general areas, scattering valuable shells with little guarantee of effect. Many of us remember how frustrating and demoralizing those reports were. An artillery shell using a standard contact fuse had to hit the target directly or impact the ground right next to it to be effective. If a group of German troops was hunkered down 50 feet away in the woods, our shell would simply plunge uselessly into the snow, and the Germans, trained to advance under cover, would simply push on. The vast expenditure of ordnance felt futile, bolstering the enemy's belief that their surprise attack was working perfectly and that American fire was proving ineffective. This mounting tactical desperation created an excruciating conflict over the proximity fuse, the war's most closely guarded secret. The field commanders knew that in that dense fog and forest, the proximity fuse was precisely the weapon we needed. An airburst shell doesn't need to pierce the fog or see the ground, it just needs to sense the trees or the troops below. It would have allowed our gunners to spray lethal shrapnel down into the enemy formations regardless of visibility. But the risk of an intact fuse falling into German hands in their massive counteroffensive was higher than ever before. Losing the secret here, at the height of our desperation, meant the Germans could reverse engineer it and deploy it against the Allies before the war was over. This left General Eisenhower facing a moral and strategic dilemma of the highest order: protect the world-changing technological secret or deploy it now to save the lives of the soldiers fighting the Bulge. The fate of the entire European campaign hinged on this trade-off between the immediate tactical necessity and the long-term strategic consequence. It wasn't until new, confirmed intelligence, suggesting the Germans still genuinely believed the VT Fuze's success was due to simple incremental improvements in our existing technology, not a new electronic principle, that the ultimate decision was made. The security risk, while high, was finally deemed secondary to the crisis at hand. The order to unleash the silent killer was imminent, and the Battle of the Bulge was about to be decided not by the thickness of the fog, but by a microscopic radar in the nose of an American shell. The crisis in the Ardennes had escalated beyond simple tactical concerns. It had become a race against the collapse of the entire front. The German advance, shielded by the impenetrable Ardennes forest and snow, was achieving critical breakthroughs, and our forces were fighting a costly defensive action, blinded and hampered by ineffective conventional artillery. This tactical failure brought General Eisenhower to the most difficult technological and strategic decision of his command: risk the world's most valuable secret to save the line. The order came down from Supreme Headquarters on December 17, 1944. In a moment of supreme strategic courage, Eisenhower authorized the immediate and unrestricted use of the VT proximity fuse for ground operations against enemy personnel in the European theater. This single command instantly transformed the capabilities of every artillery battery on the Western Front, giving our troops a technological edge that was almost unbelievable at the time. The constraint of keeping the secret safe for the Navy was shattered by the dire necessity of the moment. Therefore, the deployment was a logistical sprint. teams rushed the remaining stockpiles of VT Fuse shells, previously restricted to the defense of London, to the front lines of the Bulge. The artillery crews, many of them fighting around the clock in the cold, were quickly briefed on the new fuse, often referred to by the simple, non-descriptive term PF or by its formal name, variable time, VT. The instructions were simple and revolutionary. Stop aiming for the ground and aim for a burst height of 70 feet. This changed the complexion of the battle instantly.
Imagine the confusion on the German side. Their infantry, advancing under the assumption of safety in the fog, suddenly encountered continuous, devastating artillery fire that seemed to explode out of thin air. Our gunners, utilizing the fuse's ability to sense objects below the set detonation altitude, simply began laying down dense, fixed-box concentrations of airburst fire. The result was a continuous, lethal rain of shrapnel that fell directly down into their formations, regardless of their cover. This created a profound sense of helplessness and fear among the German troops, who reported the fire as inexplicably accurate and totally demoralizing. The deployment of the VT fuse was most effective against the enemy massing in the open or moving through the forests. The fuse transformed the density and lethality of the shrapnel patterns, turning what had been a game of chance into a near certainty of casualties within the target box. The sheer psychological shock on the German soldiers was immense. They had relied on the cover of the terrain and the weather, and now their perceived advantage had been erased by an invisible scientific weapon they couldn't understand or counter. This psychological and physical reversal was instrumental in stabilizing the American defensive perimeter and ultimately halting the spearhead of the German offensive. But the impact of Eisenhower's decision extended far beyond the immediate battle. The ability of the VT fuse to detonate above ground proved devastating in a way that conventional artillery could not match. Against personnel in the open or lightly dug in, reports indicated that the VT fuse increased casualties by 500% compared to the older contact-fused shells. This statistic alone validates the agonizing choice made by Eisenhower, confirming that the potential loss of the secret was worth the immediate massive saving of Allied lives and the preservation of the Western Front. The quick, decisive deployment of the proximity fuse at the Bulge remains a perfect case study in the intersection of science, secrecy, and high command. It secured the line, earned the respect of the field commanders, and delivered a Christmas victory, a massive surge of morale for our troops when it was needed most. Eisenhower's dice roll paid off, turning the tide of the Battle of the Bulge and marking the true beginning of the end for the Wehrmacht in the West. When the echoes of the last shots faded across Europe and the incredible logistics of war wound down, the proximity fuse, the quiet champion of the Battle of the Bulge, was often overlooked in the grand narratives of victory. It didn't boast the terrifying mushroom cloud of the atomic bomb, yet its impact was, in its own way, just as profound, and its legacy stretches far beyond the battlefield. This invention wasn't just a military breakthrough, it was a potent symbol of the intellectual and engineering spirit that ultimately defined the Allied victory and shaped the world we live in today. This technological success was built not upon superior mass production, which the Germans actually feared the most, but on ingenuity and applied science, the ability to face a seemingly impossible technical demand and solve it under duress. We honor the soldiers who risked their lives, but we must also acknowledge the scientists, the engineers, and the factory workers who risked everything to create and produce this device in secret. The VT fuse represents that unique American spirit, confronting the brute physics of artillery, the 20,000 Gs of shock, and the 18,000 RPM spin, and conquering it with miniaturization and clever structural design.
The key takeaway for those of us who remember that era is that persistence and faith in our intellectual capacity were the true miracle weapons. The German High Command had judged us on our initial flaws, but they fundamentally failed to account for our ability to innovate under pressure. The entire development process demonstrated the power of focused, interdisciplinary research, quickly turning academic theory into a combat-ready product. But the proximity fuse was more than just a wartime expedient. It was a technological launchpad. The principles pioneered by the engineers at Johns Hopkins and MIT to keep those delicate electronic circuits alive inside a cannonball laid the groundwork for the next great technological frontier. The inverted, ruggedized vacuum tubes they developed, the tiny, compression-resistant components, laid the groundwork for the next generation of durable, smaller electronics. This led directly into the development of solid-state physics and ultimately the invention of the transistor. The proximity fuse didn't just change the history of warfare, it helped launch the modern electronic age, making everything from portable radios to early space equipment possible. It was a fundamental step towards miniaturization, a concept that now defines our computers and smartphones. The story of the proximity fuse is a powerful reminder that true innovation often hides where others see only failure. We must never underestimate the power of necessity and a dedicated, clever mind. We remember the soldiers who risked everything in the snows of the Bulge, and we remember the scientists who gave them a shield and a sword that worked even when the fog was thickest. We are dedicated to bringing you these deeply researched, compelling historical narratives. We know that finding reliable, in-depth historical analysis can be difficult. Therefore, subscribing to the channel now ensures you don't miss our next story on early German jet technology. It's the easiest way to continue this fascinating journey through the past. You just have to be looking deep. We've got more stories like this lined up, and the easiest way to ensure you don't miss them is to click the subscribe button. It just takes a second, and that small effort helps our channel keep bringing these hidden histories to light.